Good morning, everyone. How's everybody today? And down in Toronto here, it's pretty gray out there. We just had a small dumping of snow overnight. It looks about maybe 8 to 10 centimeters, but not bad. So we'll go later on and shovel it. Anyways, back to this. Welcome to the lecture on infectious disease. And before we begin today's lecture, as normal, I have a number of announcements to make. And wow, look at them all. So let's get started. First, we're going to talk about the midterm assessment details, and we will be posting them. By the time you get this, it will be posted. And don't forget, the midterm is on Friday, February the 18th at 10 a.m. And that's when it will be posted on Quercus for you to start. You know, the first part, like we talked about before, it's going to be in two parts. So you have the first part, which is multiple choice, and the second part, which will be a written component. So the first part will be multiple choice, and there'll be 15 questions, and these are random questions drawn from a database, and we'll give you about 30 minutes to answer the multiple choice section. So you get 2 minutes per question, which is way more generous than you actually need. These are very straightforward type of multiple choice questions. You have to think about the answer a bit, but there's really no tricks to really freak you out on type thing. What we will be doing is locking the question after you've completed, so you cannot go back over your answers. Okay? So we do that not to be mean, but to add a certain level of stress onto you. And this kind of stress is good stress. You have to get used to this kind of stress to answer questions within a certain amount of time. So we want to keep that pressure on you. Okay? And make sure you are on a wired connection. Don't do any tests with Wi-Fi or wireless. The stability is not the greatest. And so if there are any issues, there's really not much I can do for you, okay? So make sure you contact your internet service provider if you do have any issues with your connection. And please go with a wired connection the best you can. Good. Now the written component will be about 3 questions. I haven't fully said it yet, and we're going to give you ample space in order to do that. And these will be typed pages, and we'll give you exactly how much space, how much margin, how much font, and everything else. You can use 11-point font, 12-point font, doesn't matter to me in terms of that. But we'll post those instructions by the time you're viewing this particular lecture on Friday. There are posted sample questions if you wish to check them out. These are part of the old Arts and Science exam website, so check them out. You just put 202 under the HMB 202 under the search, and you should come up with some previous exams. Now, I know those are final exams, but we used to have the exams that would encompass the entire term. And so there will be questions from this beginning term on the final exam. And so you can use those as an indicator. So it's good to check those out. Tutorials. We're going to try something new this year. And we managed to have 3 major sections of tutorials. And what we're going to do is have you upload your first tutorial assignment to Quercus, and make sure you do that by Sunday 11:59 p.m. Okay? And we're going to get you to do it via your TA's name. So what I've done on Quercus under the Assignments tab is you will see an upload area for your first tutorial, and you're going to see your TA's name. So make sure you know your TA's name. You need to know your TA's name in order to get the right box. Okay? So you have a choice of Leanne, Sage, or Sandy. So choose the right TA and add it to that. Okay, and it should be straightforward from that perspective. So give that a try. We'll see how that works out. Now I know 3 people have uploaded their assignments already. I love the enthusiasm, by the way, for that. And if you can go back and re-upload your assignment to one of the 3 TAs, your own TA, that would be greatly appreciated. But if you don't, then it will get marked and everything else, so don't worry about that. Okay, and one of the TAs will go in and do the marking on that. and I've sort of adjusted it in a way so you cannot use that link anymore. So you have to use one of those three and do it by your TA. Thank you very much for that. Now, last week's lecture kind of made an error. And so on the lymph node image, and that's slide number 16, I call it something else, lymph nodules, I believe. And so make sure, and I will reposting that specific image and calling it what it is. It's supposed to be a lymph node, so that's my bad. Okay? Now, part B of the immune system lecture will be posted along with this lecture. So make sure you go back over part B and learn the adaptive response. It's really, really interesting in terms of what happens with the adaptive response. And part A of this lecture will be posted along with part B, of course, and that will be posted tomorrow because we do these on the day before. So make sure you have a look at this lecture, which I'm assuming you are because you're listening to these announcements, and you should be fine. Okay? So this is part A of the host microbial interactions, and part B of human host microbial interactions will be posted next Friday, and that will be it for the midterm test. So everything will be posted for you by next Friday, and all that information that you have will be on the midterm exam. So what exactly is on the midterm exam? Well, we have all the lectures that we've covered, all the videos that we've covered. They're all within the lectures, and they're all fair game for the midterm assessment. Any primary paper that we have put online or website that we have linked will not be on the test. Those are for your information only. And it's kind of hard for me to decide whether or not to post a lot of these articles. So let me know, actually, because I spent last week and I downloaded a whole ton of articles. I think I got about 20 or 30 of them in around there. And I don't want to overwhelm you with these articles, but they're really, really interesting. So let me know if you want me to post some of these articles via email, and I'll go ahead and start posting them for some of these lectures that we're going to be doing. Okay? But again, those will not be on the midterm nor final exam. So none of these will be testable. They're for your basic information. They're essentially almost like a textbook. There is a resource for you for a better understanding of a specific area if you want to go more in depth within that specific area. Okay? So let me know and I can post those for you. Most of these will be review papers, and they're actually pretty good. So I'm reading some of them right now, and they're really, really good. So let me know. Don't forget, you have Reading Week coming up on February 21st. There'll be no lecture posting then, nor will there be a tutorial assigned at all. Okay? So please try and get some rest during Reading Week and do the occasional assignment, etc., understandable, but try and get some rest. Our first in-person lecture will be on March the 4th, so that will be on the Friday. And I can't wait to meet everyone. Now, without further ado, let's get on to the lymph node. I'm going to redo that slide for you. So here we have the lymph node. Now, what I'm going to talk about here is the functionality of the lymph node in the basic terms. In other words, I know you haven't had HMB 302, and in that course we go really in depth about the lymph node, but here I'm just going to show you exactly what we mean by the filtration of lymph. So let's start with the outer part of this organ. As you can see here, this is what we call the capsular layer, and this is what this arrow is pointing to in terms of the overall structure of a lymph node. And as you can see inside, we have a lot of what we call diffuse lymphoid tissue. This is all these purple dots you see. These are all lymphocytes found within a lymph node. So we call this diffuse lymphoid tissue, and it contains, as you can see, a lot of lymph nodules. And many of these are actually secondary nodules. You can actually see the germinal center in many of these. And some of these are pretty solid. Here's a nice one that's solid. Now, as you can see, from the capsular layer, we have trabecula or septa that are coming into the lymph node proper. And what this does is adds rigidity and structure to the lymph node. And it really semi-compartmentalizes the lymph node in addition, as you can see here. It's going in and in and in. And surrounding the lymph node itself, we actually have what we call afferent lymphatic vessels that are coming into the lymph node. And before we get into the functionality there, I just want to draw your attention to the major areas. So the outer part of this organ here is called the cortex. And we call this the outer part of any organ, for that matter, except for the spleen. We'll get to the spleen later on. Now, in this situation, we have the outer part of the organ, and you can see the outer part really does contain most of the lymph nodules, as you can see. You get the odd ones that go in here, but most of the cortex will have the lymph nodules. And as we go down a bit into what we call the deep cortex, or what I like to call the paracortex region. And here we have more diffuse lymphoid tissue. And this region is mainly made up of T cells. The cortex region is mainly made up of B cells, but you will also find T cells there too, but the majority will be B cells, and you'll have dendritic cells, and you have macrophages in all these regions going down and through. And the inner part of the organ, located here, is called the medullary region, or the medulla. And here, you're going to have a region, we call this the hilum region, or the hillux region, and this is where you have the entry points for the blood vessels, because you have to feed this specific organ, so you're going to have an artery coming in and a vein draining it, as well as what we call the efferent lymphatic vessel. And this is where the lymph, once it's filtered, goes out. So let's look how this functions. So around when we have these trabeculae, you can see these little white lines. And these are what we call sinusoids. And this is where the lymph travels. And so it's going to go from these lymphatic vessels, the afferent lymphatic vessels that are out here, coming into the lymph node and travel along within these sinusoids. And they're right next door to these trabecula that are found scattered throughout, these little septa that invaginate into the lymph organ proper. Now, as the lymph comes into the lymph node, it can't get back out. Okay? There's a one-way valve within that afferent lymphatic vessel. So as the lymph comes in, it's in, and as it percolates down through, it's going to see macrophages lining the sinusoids. And the macrophages are the ones that do the filtration. They're going to put their pseudopodia out into the sinusoids and take any particulates and any debris that's in there that needs to be phagocytosed and take it out of the lymph itself. And this happens along the entire journey of the lymph as it's going through. And any immunology that needs to be done will also be done within this area too. As you can see, there's a lot of diffuse lymphoid tissue, and that primary goal here is to deal with antigens. That's its purpose. So it's very easy to deal with. You're using a macrophage, which acts as an APC. And so when it takes antigens from the bloodstream out and engulfs them, it's going to basically say hi to the B cells and T cells that are within the area and say, hey, check out this. And it's going to attach it to an MHC2 molecule, and you're going to see that antigen being presented. And that's the adaptive response for that lecture that's coming out. Next, as the lymph travels down and through, it's going to get into the medullary sinuses, and it will eventually exit via the efferent lymphatic vessel, and then out and go to the next lymph node and continue up until it gets back into the venous system. So when we're looking at what we're going to do, we're going to define what infectious disease is. We're going to briefly look at some really nasty characters. We're going to go through the nature of infectious disease, and then we'll try and get through the microbial host interaction. So what we might have to do with this lecture is break it down, because it's going to be a semi-long lecture. So we're going to break it down into two parts. We'll post part A on Friday, and we will post part B next Wednesday. So what is infectious disease? A very simple, straightforward definition is it's caused by a pathogenic or infectious agent. And that, by definition, is the etiological agent. And there's a whole host of them, and we'll show you some of them very, very shortly. In addition, there are a huge number of factors involved in this disease process. And that's A, the infectious agent to begin with. B, the disease reservoirs. So where does this disease harbor itself to begin with? As we saw with COVID-19, that specific virus originated from bats. And in fact, it probably was in bats for tens of thousands of years before it made the leap, or what we call spillover, into humans. And it could have been directly from bats, or it could be from an intermediate. We're still trying to figure that one out, but it seems to be from an intermediate. The issue is we get these viruses, like a lot of these viruses that we get, like most of the human viruses that are out there, are essentially zoonotic diseases. They come from animals. The closer you are to that animal, in particular because bats are mammals and we're mammals, we seem to be getting a lot of diseases from other mammals. And this is what happens. We get them from chickens, we get them from pigs, etc., etc. So where they're located is important because it allows us to deal with that. And hopefully we can predict what's going on with future pandemics as they come, hopefully before they come down the pipeline. And this is the case also with HIV. We'll see as we go through that specific lecture that the disease reservoirs, in that case, it's the chimpanzee. And it originated from two different monkeys. And so that's the biological history story of HIV. And we're going to leave that till that specific lecture. But it's a truly mind-boggling type of event that took place there. Problem is, when you're looking at the disease reservoirs, these viruses, and bacteria too, but most of the time it's viruses, they make the leap into humans, but they don't go anywhere. Like the vast majority of these diseases don't go anywhere. But it's just that one that finds that right niche within us, and then it takes a foothold. So we're constantly being pinged by these things, viruses, etc., etc. And the issue is, how do we stop that? Well, we can't, and that's the problem. Because we're in the environment, we're part of this planet and everything else, we're going to be constantly bombarded by these viruses, etc., etc. And so it's just a matter of us gaining a bit more control over how this is going to happen. And there's so many variables. And we can talk about some of these variables when we get to the HIV lecture. Mode of transmission, that's an important one as well. How does this microbe essentially get into us? And there's many, many, many. COVID-19 seems to be very droplet spread. So it's within the droplets, and it's a lower respiratory infection. It means it goes really deep into the lungs. And we talked about how that happens later. We've done that one already, because COVID-19 goes for your septal cells especially, and it really does a number on those cells. And other viruses and bacteria have different modes of being transmitted. HIV is done through blood. And bacteria, some of them are transferred via contact, others are transferred via droplets, and so it really depends on the nature of that specific microbe. In addition, your body's defenses. If you're immune compromised, then you're at a severe disadvantage. So your body's defense systems really plays an important role. So you have your first lines of barrier. We have physical and chemical barriers that they have to go through. And if they get through those, then they go through the innate response. And if they get through that, the adaptive response. And so we are set pretty good in terms of our defenses. But if your body defenses are compromised in any way, or there's some underlying illness, in other words, there's secondary effects that can happen, then the infection can take hold. Host resistance and susceptibility, and that leads into that, especially the susceptibility part. And there may be reasons why a person's more susceptible. Usually vascular diseases like diabetes take prevalence in terms of susceptibility. And your resistance. Have you been infected already by something like this? Do you have antibodies for that? So all of this plays in with this infectious process. The agents, and there's so many of them, it's, wow, mind-boggling again. What we're going to be focusing on is the bacteria and viruses, but there are many, many others that do cause disease. So I just want to show a few of them that are listed here. So bacteria and viruses, those are the two will be the major focus. 10 most not wanted, especially in respect to the foodborne infections. Some of these you do not want. Some can be very, very severe. Others will give you a really, really bad time, gastrointestinal infections that are not very pleasant. Number one on the list, salmonella, very, very common. But there are many subtypes of salmonella. Some are okay, that will just give you a self-limiting disease, and you'll be on the bed for a few days. But other than that, you come through. But there are some that are very, very bad. And one of them is typhi, and we'll get to that one later on. And it basically causes typhoid. And the major example there is typhoid Mary, and we'll get to that later. Campylobacter, it's another one that's not very good. And that, this is the one that you're going to see quite a bit if you eat raw chicken and everything else. Noroviruses, oh, this one gives you a very, very nasty gastrointestinal issues. And you hear this all the time in the news. Whenever you go on a cruise ship, all of a sudden half the population of the cruise ship becomes infected with norovirus. And so it's not going to kill you, but it's going to leave you really wanting, that's for sure. This one's a nasty infection, and you'll be on the couch or / bed, quite a bit of pain too. Staphylococcus is another nasty one. E. coli 15787, we talked about this one quite a bit. Listeria, you find especially these two, as well as the salmonella, will be listed quite often on the Health Canada website, so be wary of those. And let me give you a hint on some of these assignments. Normally what I do is I go to the Health Canada website and I see what the flavor of the day is in terms of any recalls that Health Canada has issued for food based on what is going on. It's almost always going to be Listeria or E. coli 15787. And whatever it is, that's the one I use for the test. We don't cover salmonella in detail, so I usually don't look at that one. But these are the two big ones that you normally see quite a bit. Shigella is another one, same family as E. coli. And it's pretty nasty as well. And then you get to the bottom ones here. And we're not going to go through too much on this. This is a parasite. Then we get into more bacteria. As you notice, I've put little G's here. And this shows you whether it's gram-positive or gram-negative. And it seems to be the gram-negatives that seem to predominate. But it's not always true, because we do have gram-positives here. And the thing about gram-negatives, you have the potential for both what we call an endotoxin and an exotoxin. So those are the two primaries for gram-negative. With gram-positive, it is, most of the time, it's going to be, you got it, an exotoxin. Remember, gram-positives do not have LPS, so they don't have the endotoxin. Listeria is probably one that's a little bit different. It has no exotoxin that's associated with that we have found yet. And we do test for this and everything else, but as it stands, this particular bacterium uses a different strategy, and we'll look at that strategy when we get to that specific lecture later on during this course. Just a summary of some of these infectious agents. We've talked about Staphylococcus aureus. It's found within humans, domesticated animals. It's on your skin. It can be also found within your intestines. E. coli 15787, very nasty. This is the one. There's many strains of E. coli, don't forget. Not all are bad, but this turns out to be one of the bad ones. It's bacteria found in soil again. It's also found, hopefully not within your intestine. That's where it's going to cause disease, but there is E. coli in your intestine, ones that are not O157. It came from cattle, which is very unusual. Why? Because they don't have the receptor that this toxin binds to. And so you really don't see the disease in cattle. But when you don't do your water filtration system correctly and you have your water source next to farms, then this can have a nasty outbreak. be aware of that. And that's what happened many years ago in Warkerton. Salmonella, very nasty, comes from birds, reptiles, and mammals. In addition, there are many subtypes of salmonella, and you have to be aware of that. And one of the major ones, Salmonella enterotic, okay? And that one is usually the one that's associated with foodborne illness. And in addition, there's a subtype of that one, which is typhi, and that one causes typhoid. And we'll talk about that in a minute. Listeria, we're going to get into that one later on, so I won't mention too much. Bacteria truly is what we call an intracellular parasite. Shigella, another nasty one that really has, and the characteristic feature of Shigella is truly an exotoxin plus endotoxin. So this one can be nasty. But that's not to say that all microbes are bad, because I don't want you to get that message. You have basically what we call a microbiota in a number of places within your body, not just your intestines. You have it within your salivary glands. And any gland that has the potential for secretion of, say, bodily enzymes and everything else can have a microbiota. But usually it limits to things within the oral cavity. So your salivary glands, for example, will have its own normal flora. And we'll see other regions too. But it's mainly the intestines. We call this also the normal flora, indigenous microbiota, whatever you want to call it. It's part of your normal, basic microbiota. And really, it's organisms that colonize the body's surfaces, but they don't normally cause disease. So there's a relationship between the microbe and you. And we have two major types. We have what we call the resident microbiota, which is what you basically have right now. And it's probably been with you for a long, long period of time. Usually there's very little change, but change does happen. And if you eat, say, yogurt all the time, then you probably will have what we call a transient microbiota. They usually come in, yogurt, yeast, pills, if you take those, whatever you do, then you will have a increased population of that specific bacteria, and whether or not it becomes and stays as a resident is another story. Usually they will be outcompeted by your resident microbiota. So there's a competition that usually goes on. So that's what we call a transient. So it comes in at pulses, if you would. When we're looking at the resident microbiota, they're part of your normal gut throughout your life. And most are what we call commensal or mutualism. So what does that mean? Well, when we're looking at this table here, we have mutualism, which is really defined as both benefit. So both organism, you, or the bacterium. So if we call this the bacterium and this you, then what is being benefit? So in mutualism, both are benefiting. And so bacteria in human colon is the example that they give here. So you basically eat food. They metabolize, help metabolize some of the products, and they will give you usually a source of vitamins or something like that. So you're benefiting from that, and they get usually an alternate carbon source of some sort. Commensalism is where the organism, the bacterium, benefits, but it doesn't harm you. So you really don't get much out of this deal at all. And that's fine. You know, some bacteria like that. And Staphylococcus on the skin is an example of that. It just sits there, grows, happy, and doesn't do anything to you, doesn't cause disease, and you're allowing it to live, and it lives happy. Parasitism is the nasty version. It benefits the microorganism to some extent, depending on what goes on, and you are harmed, and that's not a good thing. And so this is where you normally have an immune response happening. In the example, and there are many of them, tuberculosis, bacteria in the human lung. No, that's fine. And we'll take a very close look at this relationship later on in a distant lecture. It's coming up after your midterm exam. And that's parasitism. And so there's a number of bacteria. We're going to look at, in this particular lecture, we're going to look at Listeria. And that's an intracellular parasite. And that one does harm. And there's no benefit. It's a question of whether the organism truly benefits, because they're causing harm within you. So why would you cause harm within your environment that you want to live? And so we'll have a look at an interesting theory about tuberculosis when we get to that specific lecture. This is an example of the normal flora found within your body. This represents within basically your small intestine. You have villi within that. And we have huge little, this is your structure here, and everything in pink is really the bacterium. And it sits on there and covers the entire area. And in fact, when you look at how much bacteria you have within, you basically, it outnumbers your total number of cells. So there's more bacteria than you have cells. That's a really interesting fact right there. This table shows you where you have microbes within your body. And there's a number of different locations that you do have it. Within your respiratory system, you have a lot within the oral cavity, and it actually decreases the further down you go, until you get to the ultimate down to the alveolus, where they are, it's what's called axenic. And then essentially you have no natural microbiota there. One of the main reasons, well, there's actually two reasons really. One is that the macrophages found within your lung and around the alveoli, and these are resident macrophages, we call them dust cells, are very efficient at getting rid of any bacteria that are there. And most of the time, if you do have a bacteria that's going to be there, it's there, Streptococcus, for example, especially if it's Streptococcus pneumonia species, then that could lead to infection. And so your lungs are kept very, very clean from that perspective. I mentioned there could be a second reason. Well, the other reason is that we may not have really the culturing mechanisms to essentially find the bacteria if they're there. And that could be another reason. We could discover that we do have some bacteria that are living there. Don't forget to read that paper on that teisobactin. It gives a new way of isolating microbes. It's a very interesting way to do it from soil, some that we've never done before. So they're always coming up with new techniques to isolate bacteria. And this could be just the case of it, we just haven't found it yet. Maybe in the future, but I'm not really holding too much against that. In the upper digestive tract, we have a huge series, and then as you get lower into the small intestine, then it goes down, and then when you get into colon, it goes up. And there's reasons for that. We'll have a look at that later on as to why that would happen. We have it within other regions of your body. And the one I like down here is your eyes and skin. You have on your skin quite a number. And then when you're looking at the conjunctiva, which is basically underneath your eyelids, there's only very few Staphylococcus. And it's kind of interesting because tears wash, and this is the mechanical barrier, if you would, that kicks into play. Tears basically washes most of the microbes from your eye. So very effective from that perspective. Very interesting. So the natural or normal microbiota normally is fine most of the time. But you have to remember, they can be opportunistic. In other words, if something happens, if one of these microbes get into a place where it's not supposed to, then it can cause disease. So in other words, if you become immune compromised for any reason, then issues can arise. So you have to be wary of that. And they're just doing what they normally do, and they want to grow and grow and grow. And so that's what they do. And if they get into an environment that allows them to flourish, and you invoke immune response to that, then that can lead to disease. Immune suppression is probably the number one right there. And changes in the different types, maybe the abundance of different types, can cause disease down the road. So you have to be aware of those conditions. Typhoid Mary, and I really encourage you to go to this website. It's Wikipedia, and it shows a story of Mary. And she basically was an undetected case. She had very active germs, and basically these germs, specifically bacteria Salmonella species, Enterotica typhi, was in her, and she spread it through foodborne preparation. She was famous for what was called the peach cobbler, and if you actually cooked the peach cobbler, nothing would happen, but it was basically raw food that she was giving people, peaches, plus a little bit of dough and everything else. And that spread. It really spread through a number of people, and it killed a number of people too. She was quarantined, and she escaped because she didn't believe what was going on. She said, "No way, you're going to put me in quarantine." And she, again, started to cook for other people, and she did it again. She spread this bacterium through other people because she wouldn't wash her hands, and it spread. And so people got infected, and some more people died. And then they got her again, put her in quarantine, and she died during quarantine. And when they did the autopsy, they found this bacterium living in her gallbladder. And so it's a very, very sad case. But she wasn't the only one. There were many people like this. So have a look at that. It's a very interesting read. And in addition, when we get to the HIV lecture, and we're going to also listen to a podcast. And the first part of that podcast is on Typhoid Mary. And it goes through quite a bit of political background, if you would. That's not very nice. And so, although we won't cover it during HIV, we'll have that posted for you. And if you wish to listen to that component, go for it. It's actually a very interesting listen. So the movement of microbes into hosts. Basically, we have to give you a few definitions. So we're at the exposure to microbes stage. So we're getting ready to look at this infection process, exactly what happens. And there's three major definitions. One's a bit controversial, but I'm going to define them as we have right here. And people really don't like the word contamination for some reason. I don't know why. So contamination is literally the mere presence of microbes in or on your body. That's a simple definition. That's perfect. Colonization, this is where things get tricky, because most people think contamination is colonization. It is not. And so colonization happens when conditions are right for bacterial growth. And usually they grow without causing any disease or infection. That's fine. So basically the mere contamination, the mere presence, is literally you getting touched by somebody, and whatever was on their finger that touches you usually deposits bacteria on you. And so that's contamination. It's the mere presence of these microbes on you. If they get a foothold and the conditions are right for growth, then they colonize. They start to grow. So they're forming a colony. It's colonization. Infection is when the organism evades your external defenses. So both the physical as well as, you've got it, the chemical. Once those have been breached, then they can get into you, grow, and they become established within the body. And so infection can take place. Well, that's pretty amazing. Routes of entry. Remember we talked about this a little bit earlier when we were looking at the diffuse lymphoid tissue. And I told you that anywhere you have an entry point, you generally have some sort of diffuse tissue ready. Not all places, but we do have some entry points that may have it. So for example, the ear doesn't. Conjunctiva of the eye, usually they don't have diffuse lymphoid tissue there. Your nose, mouth, it does. Placenta, vagina, in males, penis, urethra, anus. So some of these regions do. So whenever you have and you look at the oral cavity and you proceed down your tube all the way down and through to the anus, you're going to find diffuse lymphoid tissue throughout. So any tube that's basically an external environment like your digestive system is, when you think of it, then you're going to have diffuse lymphoid tissue present. And that starts right in the oral cavity as your tonsils and progresses down and through. But there are other aspects too, broken skin, insect bites. These can all be entry points for microbes. So you have to be aware of that. Remember this. Why? Because we're going to show you exit points later on. And you're going to see how many of these actually line up. And you'll find that out near the end of this lecture. The role of adhesion is critically important. And that's why we went through all the adhesion molecules that we talked about earlier. What do bacteria have that aid them in adhesion? That's the important part. So it's the process by where microorganisms attach themselves to your cells. Literally, they want to bind to you. So they have a variety of different ways to do that. Pili, fimbriae, just to name a couple. What's another one? Think about it. Yeah, the capsular layer as well. Pretty interesting. They need this to really establish colonies within you. So without the binding, without being stationary within that area, chances of them being infectious is greatly reduced. So they use these adhesion factors, the adhesion, very, very specialized structures, attachment proteins. And we're getting to the receptors very, very closely. So when we're looking at the microbe itself, it has basically structures on them, call them a ligand, that binds to specific receptors found in us. And these are usually, membrane-bound proteins that has a little sugar coating right on top, and they recognize these specific sites. Well, it's only fair. Basically, we make receptors to them. We bind them, we actually chew them up, and present some of these epitopes on the MHC molecules. So they reciprocate, basically, and they bind to us, get into us, and they cause disease. This is how we evolved, basically, this tit-for-tat relationship that's going on. And we've come up with this series of defenses that allows us to deal with these microbes. Well, hopefully anyways. So the receptors that they bind to, as you can see here, really have no role within their, quote, metabolism. They're just using these receptors to either gain access to our cells, or they use them to start their infectious process. So for example, the SARS-CoV-2 virus binds to the ACE2 receptor. Well, normally the ACE2 receptor in humans deals with cardiovasculature, etc., regulation. And within this virus that binds to it, it's not involved in that pathway at all. So it's using that specific receptor to gain access to our cells. And that's the whole basis of the receptor binding. It triggers an endocytosis, the virus gets into us, and then causes disease. And we'll see how that happens when we get to the virology section of the course. So in this particular case, the microbe, bacterium, is binding and it's going to elicit a response somehow. And in fact, not all microbes bind to us specifically. E. coli actually brings its own receptor. It has a type 3 secretion system, secretes the receptor into you, the host cell, and then these receptors essentially go to the cytoplasmic surface, and then the microbe binds to these, and then establishes a colony that way. Who does that? You bring your own receptor. That's really, really interesting. Listeria will bind to specific receptors on the host cell, and as it binds, it actually enters the cell via a zipper mechanism, and we'll take a look at that zipper mechanism in a little while. And it really just, all these receptors start coating the actual microbe, and it just slowly brings that microbe into the cell itself. And that's how Listeria gets into the cell. So not all these microbes need to get into the cell. Some do in order to evade our immune system, etc., but some don't. They just sit on the surface, colonize, and they're able to cause disease. So a role of adhesion is really important from that perspective. And again, found on many viruses and bacteria, and it's that host interaction. So we have, and when we get to the viral section, you'll see that they refer to these as keys going into the locks, where the locks are, just a door lock, for example, is found on the host cell. The key is that protein that sticks out of the virus, or in bacteria, doesn't matter, and it unlocks that key and allows you to get into that host. So that's the key host, the lock interaction. If we change or block the ligand or receptor, we can pretty much cause a prevention of the infection. So that's an important consideration. If we can change it in some way, mutate it, then we're fine. But most of the time we need those receptors because they're actively involved with our normal metabolism, like the ACE2 receptors. We need that. And so in order to prevent that interaction, it's always best to change the ligand on the virus or bacterial surface if we can. And sometimes that's very, very difficult to do. That's why instead we go for vaccinations. It's a much, much easier way to deal with a huge population. If we get a good vaccine, then that will trigger your immune system and allow the immune system to do its job and get rid of the bacterium. So it's an easier way of doing it. So if the microbe can't bind, then basically it's going to render this microorganism what we call avirulent. So the nature of that disease will be much, much, much less. Good. And to end off, don't forget about biofilm. This is where bacteria can actually bind to each other. So when they form this slime layer or capsular layers, they can generally bind to each other too, and that gives you what we call a biofilm. And that can be quite nasty. We do see this accumulation within medical equipment sometimes, but also the textbook example is basically your teeth, where you get this biofilm that forms if you don't brush your teeth on a daily basis. So brush your teeth. Or do the experiment. Don't brush your teeth for a week and see what happens. Don't do that. It's not very good. This is dental plaque. So this is what we just talked about here. This would accumulate on your teeth. And this is a very small amount. Imagine if you didn't brush your teeth, you would have very, very thick amount of dental plaque. So now we're getting more into the nature of the infectious disease. And in order to get you to understand a bit more what's happening, we have to go through a couple more definitions. And you're going to see these words, these terms, symptoms, signs, and syndromes, quite a bit, especially symptoms and signs. If you're a Wikipedia person and you look at disease on Wikipedia, normally what they'll do is they'll have a section that has the symptoms and signs. And so defining what those mean tends to be a little important. So a symptom is really a subjective characteristic of the disease. And this is really felt by the patient. So we're talking pain, nausea, headache, chills, versus signs, which are objective manifestations. In other words, you can actually measure or really see what's going on. You can visually see swelling. You can see projectile, and you can see shivering versus chills, which may not be evident. So the way I remember it is